So yes, I'm an assistant professor of computer science at the University of Illinois right now, but the work I'm presenting is the research I've been doing at CMU over the past year when I was doing my postdoc. So this is truly a team effort work with an awesome list of co-authors, especially Akarsh and Arthur as the co-primary authors. So this work wouldn't have been possible without their contributions. So as a driver, we are usually forced to drive in very bad visibilities, like dark nights, like at foggy or rainy weathers. So automotive radars in this case are really helpful because of their robustness to different weather and lighting conditions. However, looking at RF images, especially coming out of these commodity radars, they're very crude, especially compared to our RGB cameras where we have a lot of details. So we're missing these details in the RF images, especially that person walking the street. So we asked, is it possible that the objects themselves can tell us what they are and where they are? And that naturally led us to backscatter communication and RFIDs. So if we look closely at a structure of a tag, it's nothing more than an antenna connected to an RF switch. And the way it communicates with the reader is through that RF switch. When the switch is off, the received signal will be absorbed by the load attached to the antenna, or you just use it for energy harvesting. But when the switch is on, it's like the antenna is shorted, so any received signal will reflect back from the reader. And that's how these RFID tags are communicating with the reader, sending 0, 1 bits by switching on and off. But the important thing is that this whole operation is independent of the signal frequency or the waveform. Yes, we still need the antenna and all the components to be tuned to that frequency. But other than that, we can basically say intuitively, we can just replicate that circuitry and have an RFID tag that works with automotive radars. But here's what makes this really hard. Automotive radars operate in millimeter wave frequency range, and as probably all of you know, we have significant path loss to deal with. And in this case particularly, we're trying to detect the reflection from a very tiny tag as opposed to that gigantic car that is all made of metal. So it's even more challenging to basically detect that reflection coming out of the tag. So the main question we're trying to answer is how can we break that trade-off and build like a millimeter wave, long-range millimeter wave tag? So there are two enabling insights that we basically use in this work. So number one thing is in backscatter systems, all we need is to differentiate these two channel states as the tag switches on and off. And in each of these states, the tag presents certain radar cross-section. And so all we need to do to increase the tag detectability is to increase this differential RCS. And if you look at the formulation for differential RCS, you see that it's inversely proportional to the wavelength, meaning that if we can keep everything else in this formula fixed by just going to higher frequencies than like smaller wavelengths, we can actually increase the tag detectability. So at least so far, theory is not against us. But that's not enough. We still need a minimum of energy from the tag to be able to detect the tag, detect the tag. So that's here where it comes the retroreflectivity. So we designed these tags such that instead of reflecting the signal in all directions, they retroreflected toward the direction that the signal comes from. But we're doing it completely passively. There is no active beam forming or phase shifter at the tag to steer the beam. So this way we can push the performance in 3 different axes. So the tag is very low power because of the simple circuitry. So with a 3-volt lithium battery, it can constantly operate for more than 20 years, or you can just have a small solar panel and just use energy harvesting that way. We could detect these tags from very long ranges, like 100 meters or so. And at the same time, we can detect these tags with centimeter level accuracy across all those ranges. We call this system Millimetro, and you can imagine these Millimetro tags attached to the road signs, pavements, back of the bicycles. And then with these radars that we already have in the car, we can detect them, identify them, and localize them. So some of the key features of Millimetro, to get ultra low power consumption, you see that the tag circuitry is very simple. We just have an RF switch to do that modulation or switching on and off. So the tag is really dumb, so it doesn't do anything. And we just draw that PWM signal from the MCU, and the MCU is always in the low power mode. To get retroreflectivity, we use Venato arrays. That is basically a specific arrangement of antennas. So what you see in this picture is like pairs of antennas connected through a transmission line. And all we need here is to design these transmission lines to have the same length or just multiple of wavelengths different. So the way it works, the signal hit the tag, it goes through the transmission line, reflects back from the other side, it goes both ways. And if you look at the phase shift across these antennas, for the incident signal and the reflected signal, they are just inverse of each other. So it means with whatever angle the signal comes in, it reflects back with the same angle. And that's how we get retroreflectivity. So in our current implementation, we have these modular Venato arrays that basically allows us to try different number of elements or different modulation frequencies. So we're basically doing a lot of engineering to make it work. But long range is not the only thing we need in automotive application. We also need very low latency. So as the car passes by these tags, it could detect it and localize all of them. So how can we get low latency? So we design a tag reader communication that is completely asynchronous, meaning that we have a tag that is constantly switching on and off. It's not particularly listening to one reader. A car passes by, it sends the signal, gets a reflection, and independently tries to detect the tag. So as opposed to traditional RFID systems, here we don't have any coordination or handshaking between the tag and the reader. So the bonus feature that comes with that is one tag can respond or retroreflect the signals from multiple radars simultaneously, or one radar can simultaneously read multiple tags. So we have this concurrent operation just as an organic feature of this asynchronous protocol. But the result of that asynchronous protocol is that we're now shifting all the processing burden to the radar side. So how can we detect these tags when there's no coordination between them? So assume that we have like a radar sending a bunch of chirps. We receive the reflections from objects in the environment, including the tag reflection, and you see that modulation pattern for the tag reflection. So the first thing the radar does, we do a down chirping, which is basically subtracting the sum of the received signal with the transmitted signal. And then we apply a simple FFT on top of that and get this range spectrum. So here you can actually see the modulation of the tag, and it's like we have applied a square function on top of the tag reflection because the switch is turning on and off. So sometimes you have the reflection, sometimes you don't have the reflection. But because of that asynchronous protocol, you can easily detect it in the time domain. You don't know when the tag is on or off. So we do another FFT across the chirps. We get this range Doppler spectrum. And now we know that the FFT of the square function is a sinc function. And then the peaks of that sinc function are basically harmonics of that modulation frequency. So all we need to do now is to do a matching filter between like that sinc function across all these range bins and find out where exactly we see the modulation pattern of the tag. And then we can apply the same thing across the antennas and then get the angle. And so with range and angle, you can exactly locate where the tag is. Okay. So, the other thing that I should mention here, so what if you have multiple tags? How can we differentiate them all together? Since we shifted all the computation to the frequency domain, all we need is just different modulation frequencies, like how fast the tags are switching on and off, and then have those frequency components of those six functions just to fall in different bins. And that's enough to basically be able to differentiate different tags and identify all of them. So we evaluated this system across different environments, both indoor and outdoor. We also tested it for different mobility cases where the radar will walk with the radar or have it on a bike or car. We also tested it in different like non-line of sight situations, because especially for outdoor, it very much happens that you have some obstacles between the reader and the tag. And we see that across all these experiments, we get about 15 centimeter localization accuracy. And then we can detect these tags easily up to 100 meter, and then it slowly degrades as we go further from the radar. Here's a snapshot of ranging the tag in the mobility cases or a case where we have multiple active tags. So we also tested it in different penetration cases. You see, like when we have the tag behind a drywall, concrete, and across all of them, we can preserve that centimeter level accuracy. Of course, it's worse at some points, like concrete. Like in some of the concrete examples, we actually have 4 blocks of concrete between the tag and the reader. So just the speed of transmission inside that concrete changes, and that could be one of the reasons we have higher error in that case. Here's the concurrent operation. We tested it with like 6 active tags, or for example, 4 radars, and we see that across all of them, we can easily differentiate them. And we have all other like a simulation kind of processing on what is the number of active tags we can support with this modulation and this coding scheme. So check out our paper for more details on all of that. So here's just a few demos of like showing how the system works in some of the experiments with it. Like the pink dots is the estimated location, the black ones are the ground truth, and you see as we're approaching the tag, we can keep following the where the tag is. In this case, the tag is actually inside the closet in a non-line of sight situation. We also have this augmented reality app that we design on top of Millimetro, so it basically uses the estimates and visualizes where the tag is, and you can see that we could also detect it even through the walls. Or here's the case where we have multiple active tags, and we use the same app to basically visualize all those active tags together, like where we estimated their location, different colors or different IDs of these tags. So if you're interested in seeing more of these demos, check out our demo presentation. This awesome undergrad student who's here now, so we'll be presenting the work and the AR app. So check it out this afternoon. So yeah, so if you just step 1 layer higher, you can think of Millimetro as this industrial grade QR codes, but now in RF domain. So these RF coded markers could work in different lighting or weather conditions, and we can preserve that centimeter level accuracy in very longer ranges than QR codes. So I think that was all I had for today. I'd be happy to answer your questions.
Hey, hi, I'm Kshitij from UCSD. That was a great talk. So my question is more about the engineering aspect of it. So we know while designing these tags, 2 most important aspects are long range and retroreflectivity. So my first question is that we know more antennas in a van at our arrangement will give us more retroreflectivity. Then why did you go with a 2 antenna design?
So you saw that, I think one of the slides I had like a bigger antenna array. So we've been trying different number of elements. Most of the experiments and the results we show is 2 elements. That's basically the minimum amount of performance you can get with a retroreflective as opposed to like a regular antenna arrays. But yeah, the larger antenna array you have, you get more directionality on the with the retroreflectivity. But at the same time, it gets a little bit harder to design those retroreflectors that are larger elements, like how you design you need to get a really good phase coherency between all those transmission lines. So you have a little bit of noise added to it. And also you're losing the like a small form factor of the type gets bigger and bigger. So yeah, so no limitation on why going with 2 versus bigger. You can definitely go with that. It's just a matter of designing like engineering.
I see. Great. Just a follow-up question. So also, should we optimize for the individual gain of each antenna, or is there a combined effect that we should optimize for?
Yeah, that's a very good question. So if the individual elements have higher gain, of course, it helps retroreflectivity as well. But on the other hand, the issue is if you have a really like a high gain antenna, you have to make it directional. And if you make it directional, you're basically losing the field of view of the tag. So in this case, like I think you had a picture of that in one of the slides. So we actually decided, especially in automotive, the vertical angle is very short. You don't have to really cover like all the 180 degree, but horizontally, you want to at least be able to cover the road area. So we designed these 4x1 elements. We have like very wide field of view on one angle, but we have limited field of view in the vertical side, but also higher gain because we're using antenna array. So yeah, so the challenge is the trade-off between directionality of that individual elements in the van array and the gain you can get.
Thanks a lot.
Hi, Lahi. This is Yaman here from EW Madison. You mentioned that each tag has a certain unique frequency. Was there a basis behind the choice of those frequencies, and what was the impact of, or what was the maximum, minimum, and the
Yeah.
impact of these?
So one thing I want to clarify, we're not using like frequency hopping or dividing the bandwidth. It's just the frequency of modulation, how fast you're switching on and off. And yeah, as I said, the only metric you have, you want to make sure that you have enough separation between that frequency component of the sync function that will be resulted from that modulation speed. So that's the only requirement we have. And like it's a function of the number of chirps you're using in a frame, or what is the bandwidth you have in the system, like what is the chirp duration. So I think we have this analysis in our system that if you go with the like completely orthogonal codes for the tags, we can support, I think, 24 tags simultaneously, but that means like all the harmonics of the sync function are completely orthogonal across all the 24s. But then you can start releasing some of those restrictions on, for example, you allow some overlap between the codes, but you can still detect them, because the challenge usually is when you have two tags exactly falling in the same range bin and have very similar modulations, so modulation frequencies, and that would be really difficult to detect them. But if they are far from each other, like falling in different range bins, but they have similar modulation frequencies, you're still able to differentiate them from each other. So there are use cases where you can release some of these requirements to support larger number of tags, active tags. And yeah, we have that analysis in the paper that you can go up to 100 active tags at the same time, depending on like how you're dealing with those trade-offs.
A quick follow-up: is there a certain theoretical limit to the maximum scale you can have with the current setup?
You mean on the number of tags?
The number of tags, yes.
Yeah, so limitation is basically the bandwidth you have. So in this case, yeah, we were limited with 100. More than that would be difficult to basically be able to define. The Doppler bins you have to be unique at some point. Either you need a lot of chirps to be able to differentiate them, or you need a very high sampling rate that we didn't have with the radar we're using.
Perfect, thank you.
Mm-hmm.
Hi, I'm Shreya from RISE. So I have a very generic question, that you're using frequency peaks from different tags for identification. So do you have any security concerns for this identification technique, if there are, because you just completely get rid of the handshaking between reader and tag?
Yeah, that's a very good question. And yeah, this is not something we address in the paper, but we are actually working on a follow-up on how you can authenticate the tag. It doesn't necessarily have to be on that communication protocol between the tag and the reader. Like you can basically pick the modulation frequency as a pseudo random number. So it's not always the same number. It's a frequency that only the reader or the radar and the tag knows, and you know that it should be what you're saying, and like use the authentication as a way of making sure this is the tag you should talk with, and not like someone else attaching their own tags to the system. So we're basically considering other alternatives, because I really believe that this is the right protocol. Like if you're using backscatter communication in general, let's say I want to bring internet connection to all objects. Yes, then you need to have like this like envelope detectors and a more complicated circuitry. But in a case like this, where we are using the tag like a QR code, it's always sending a fixed code, then you don't necessarily need to deal with all those like synchronization between the tag and the reader. And so there are other opportunities of making it secure, making it like robust and all of it. Yeah.
Thank you.
Mm-hmm.
This is the last question.
Yeah.
So in one of your figures that you showed earlier, the tag can be put on a robotic hand. So, but I think in this case, all the experiments so far, the tag is in the static location.
This one, no. So this is constantly, I think all the mobility experiments with it is the radar is constantly moving toward the tag, going away, like with different angles. And so it's not like you need to have a fixed location of the tag and the radar to detect it. So one thing I didn't actually mention, when the tag, or either the tag or the radar is moving, you also have the Doppler effect on top of the modulating frequency. And we're actually talking about that in the paper, where we're simultaneously trying to find the modulation frequency and the Doppler frequency because of the motion. So the match filter we are applying is with the consideration of Doppler because of the mobility, and we can take care of that. And in all of these cases, we just process each frame individually, not like using a bunch of frames all combined together. So the tag could be easily moved. And I think the time in terms of like the chirp duration is like in the order of milliseconds. So we can still localize the tag instantly.
Thank you.
Cool.
Thank Alahej one more time, everyone.